Just recording capture your screen. I hit the camera. Okay, slideshow. Okay. Thank you for coming here. Thank you everyone offline and online. Welcome to ACM UC General Body Meeting 8 on today, November 17. Please fill out our attendance at acm@uc.org/c so we know who joined and who's eligible for voting at the end of semester. Next semester. For newcomers, ACM at UC is the student chapter of the National Association of Computing Machinery, but in simpler terms, we are basically the computer science and programming community at UC. We're trying to foster a community around the common interest in computer technology, software, and hardware. To any majors are welcome as long as you have passion in technology. Our mission is to encourage professionalism among tech enthusiasts in a collaborative fashion by facilitating learning beyond the scope of classroom and develop your innovative and inclusive ideas. So we do that through a variety of events like guest speaker, panel general bodies like today with Dev. We do it through ICBC is the programming contest, and Revolution UC is our upcoming spring hackathon. Also have a Discord community and recorded meetings. So yeah, just attend 2 meetings and remember to check in and you want our membership. You do not have to pay for ACM National. The code of conduct, ACM UC is dedicated to a harassment-free experience for everybody. Our anti-harassment policy is on our website, and we also follow the UC code of conduct, including any non-harassment and anti-discrimination statement. Okay, if you have not already, please join our Discord now. It's the best way for us to connect with you, for you to connect with us, enjoy on amazing events. Even exclusive event we have on our Discord. We have a ton of channel when we looking to expand on this, so join our Discord and probably give it a few suggestions too. I'll give it some seconds. Cool. Thank you. Yeah, join our campus link. And that's say we're gonna go to the main thing today. Please welcome Dev, IT student and former president of ITSA, to talk to us about modern cloud services. Yay.
Thank you. Go to the slides here. Okay. All right, so welcome everyone. We are going to talk about cloud services, modern cloud services. My name, you can call me Dave or Dev. Most people end up calling me Dev anyways, so that's fine. I'm a fifth-year IT student. I work at the IT Solution Center as a software developer. Here are my socials. And as of recently, I've also started a YouTube channel. So if you like the content tonight, you will also like my YouTube channel quite a bit. I'll also try to, sorry, go ahead.
How many subs?
Pretty close to 2,000 now.
Yeah.
Thanks. So yeah, I'll also probably take this talk and chop it up, put it on my YouTube, so you can watch it there later, or you can watch it on ACM's YouTube. So let's talk about cloud services. Cloud services have been pretty simple from the beginning. It's infrastructure that's managed by other people. That's it. It was true for the very first cloud service. It's true today. The only thing that's changed is the meaning of infrastructure. And throughout the course of this talk, we're going to discover how. So infrastructure started as just bare metal or hardware. So you would go to Amazon, you would say, I need a virtual machine or I need a physical server, and they would give you one. or like they would run one for you, and you can install and run into it whatever you want. But it has now evolved into specific capabilities. For example, there's a cloud service that you can go and say, I want authentication and authorization for my app. And it would give you not only the hardware instances that the service is using, but it would also give you the software that's running on that basically performs all the authorization stuff for you, and you just have to hook into their system. This is a useful model this is a model that's useful to kind of think about these services. At the very bottom, we have the bare metal or the specific hardware. On top of that, there's an operating system that you can install into it. It could be anything from Windows to Linux to maybe even Mac if they decide to open source it or make it freely available at some point. Then on top of that, there would be dependencies that you would have to install in that machine for your code to run. For example, you might have to install the C++ compiler. You would need a Python. You would need Node.js. You would need Git. You'd probably also need Make and a bunch of other things. If you are doing some sort of image or video processing, you would need codec libraries for those. And then finally, on top is the code that you write, which is your application. So we are going to use this model to kind of like get a good idea of what cloud services are doing for us. If they're not helpful, don't worry about them too much. So once again, let's start with bare metal. What is that? Servers and networks. That's pretty much it. Or more likely, it's going to be virtual machine instances. So you would go to something like AWS or Azure or DigitalOcean. You would say that you want a server, and you would be given a virtual machine instance that you can go into. You can install whatever. You can run whatever. Yeah. They come in different shapes and sizes. So the most familiar I'm with is AWS. So that's the one I'm going to use the examples for. There's a general purpose machines that are basically jack of all trades, master of none. Then there's a category called burstables, which are basically, they have a limited computing power, but in case there's a bunch of people using the application that you're hosting on there, its compute capacity will just like burst for a short while, and then it will go back down or like whenever you run out of burst credits. So they're pretty useful if you're building something that you're expecting a lot of people to use at some point. Then there's instances that are optimized for either memory or storage or computation. For example, if you want to install and run a database in one of these instances, you would probably use the storage optimized one. Or if you're running a machine learning model, you'd probably want a computation optimized one. Speaking of, you also have GPU instances. So they are a little more expensive, but if you just need access to like GPUs to do some computation for a short time, you can do that. And also you have different CPU architectures. You have Intel, you have ARM architectures, everything. And of course, you have access to networking. So you can specifically define how these different machines or virtual machines are going to network with each other. So you can like have pretty big network charts all in the cloud. And pluggable storage. So basically, you can have two different machines, and you can take the storage of one of the machines, plug it out, and plug it into the other machine. That's possible to do. I don't know how, but that's something that you might want to do if, let's say that you want to get some data out of a machine, or just look at it without like going into the machine or without like disturbing anything that's going on into it. You can use that. This is what it looks like on the model that I shared earlier. So the only thing that this type of cloud service will handle for you is the bottom layer, which is the specific physical infrastructure. Everything on top of it is something that you have to manage on your own. So why would you use something like this? Well, it's pretty simple. If you want all that control that's given to you, if you desire that control, then it's a pretty good thing. If you have a very small, a very basic workload, so you can just go and get a virtual machine, install whatever you want on it, and just run it and be happy. You don't have to think about anything else. Or if you have extremely huge workloads, And by extremely huge, I mean you need 60, 70, or even 100 of these servers running. In that case, this would be the cheapest option compared to like some of the other stuff that I'll talk about in this talk. But I don't think any of you need 70 servers running, right? Cool. Maybe. In that case, yeah, go for this. This will also be useful if you're moving from self-hosted to the cloud, because self-hosted, you basically have none of these. You're managing your own infrastructure. You're managing your own hardware as well. So if you want to go from that to cloud, baby steps. So that's really the only thing that exists in the basic basic infrastructure phase. So we can talk about capabilities a bit. So
renting a AWS instance operating system with those.
It gives you the operating system, but you have to choose what operating system it is, what version it is, what else comes installed into it. So yeah, they would like give you an instance with some things installed, but you still have to go through the process of deciding which one of those you want. Which we'll see that that's not the case with some of these other capabilities. So compute makes sense. You just write some code that will run. These usually come in form of containers. So if you don't know what a container is, you can basically think of containers like virtual machines. They are isolated environments that you can install and run whatever you want. But they are much more lightweight, which means you like in your regular laptop, you can run probably 5 to 10 containers. And on like cloud servers, you can probably run hundreds of them. So usually with containers, what we do is that let's say that I want a web server, I want an API server, I want a database. With bare metal, what I would do is that I would probably just have one server and install all those 3 things on it. But with containers, I'll have a separate container for all 3 of those things, and then all 3 of them will be separately deployed. This offers a pretty nice abstraction to work with cloud. I'll go more into it later. But the service that the cloud can provide here is a managed platform for running those containers. So for example, you would just give it, you would just go to the cloud service, you would tell it to run a specific container, and it would start and it would run it. It's almost always like pretty automatically configured. Like you can just click on a couple buttons and the platform is ready for you and the container is running for you. They also have this thing, build packs is something that Heroku introduced. Now it has like kind of gone out of fashion. But basically the point is that it can detect what programming language, what framework you're using and automatically do everything for you. If you have a Django project, it would automatically spin up a container with PHP and all the dependencies installed. It would automatically install all your application dependencies, which I think it's pip install. That's it, right? Or for Node.js, it would be npm install. It would automatically clone your project into the container. It would install, it would build, and it would start it. So it can do all of that, or most services can. They're automatically scalable, which is probably their best feature. So if I have 5,000 users using my application and it's getting slow, I can just tell these services to spin up two instances of my application. And now they're both running, they're both getting 2,500 users, which is much easier to manage. And if I have more users, I can have like as many instances of my application running as I want. Now, why would you want this? They're pretty great for granular services. So like I mentioned, if I want 3 separate things, I want a web server, an API server, a database. Or I can maybe even split up my API servers into 3 different things. So if I'm building an e-commerce app, I can build a separate service for product catalogs. I can build a separate service for placing orders. And I can build a separate service for inventory management. And I can deploy them all separately. And I can scale them all separately. This also has some of the least like manual configuration required. You can just write your code in whatever application you use, and you can go to the service, point it to your GitHub repository, and it can deploy it for you. Easy to set up. And this is where it would lie kind of in that model. The orange here means that you would kind of think of it, not too much, but basically like Bao asked before, this one you don't have to think about what operating system it's running on at all. You just write your application code. You kind of have to define the dependencies of your application, and then the cloud service takes over. Yeah, I'll get to that soon. Oh yeah. So the question was, let me quickly go back here. But when I was talking about this, the question was that don't services like EC2 also manage the operating system for you? And the response was that we still have to think about the operating systems, which system to install, how to upgrade them, which ones does our app support, things like that, which is why it's not highlighted in green. But technically, you just have to like click on a couple buttons and it comes with the operating system installed in the beginning. So yeah, at any point, if you have any questions, please feel free to like raise your hand, interrupt me, or just unmute and speak up if you're on Teams meeting. I don't see the chat here. So yeah, that's about compute. Let's not talk about storing some data. Fully managed database as a service. So once again, instead of renting a virtual machine and installing a database software on it, you would just go to these services and say that you want a Postgres database or you want a MySQL database, and you would have to maybe define a few basic settings, and then it would give you a URL that you can use to connect to your database. And this is available for almost all types of databases, unless they are extremely niche. And by that, I mean general purpose like Postgres, MySQL, SQL Server, whatever they are. Specialized databases, so document databases like MongoDB, graph databases, search, time series, key value, whatever exists. Pretty much almost all of them have a managed cloud solution. There's also file storage, which I initially had a different slide for it, but I decided to just fit it in here because it's kind of the same thing. File storage where, again, it would give you some basic API to upload and then later download some files. And it's extremely cheap compared to, again, renting virtual machines. Then there's also a type of a database called data warehouse, where you can store a lot of data, but it has like a much higher cost of access. So you would use this to like kind of dump a bunch of data that you later want to process. And on the opposite side, we have caching, which has a lot less capacity for data, but it stores it in memory, so you can access it really fast. So you would use it for caching purposes. Why would you do this? Once again, less or no setup. You're not installing database. You're not installing containers. You're just asking for a database, and you're getting it. And because databases are really hard to manage, if you've ever wanted to be a database administrator, please don't. Or if you do end up being one, please be really, really good at it, because the rest of the world depends on you. Because you have to manage things like scaling. If the databases are really hard to scale, like you cannot just have three different machines running the databases and expect them to just synchronize with each other. You have to manage that. Availability, backup, security, they're all big problems with data. And then here is what it is. What's up?
I've also heard that
migrations for databases on cloud is much easier. What kind of migration? Like moving from on-prem to cloud, or like? Yeah, I would say so, because database is like migration is difficult for applications because you have to change your code to a lot of extent. But with database, you don't have to change anything. You just have to point your application to a different database. So really the only thing about migration is migrating your data over, which like cloud services have a lot of like providers to do that. Like they can literally send you physical hard drives where you would put your data and you would mail the hard drives back to them. Yeah, a lot of like huge data centers opt for that. It's faster than network transfer, which is expensive. Does that answer your question? Awesome. And yeah, here, so these services don't very neatly fit into this model. So I just decided to make it like this, where you don't have to think of any sort of like dependencies for a database. You just get your database and then you write your code on top of it. Content delivery. So this is the fun one. This is usually used for static assets hosting. So your websites, your images, videos, fonts, any kind of media content. These are edge distributed, which basically means that they are available in a bunch of servers around the world. So usually, like if we are here in Ohio, we are making websites, we're using cloud services, we're probably using US East 2, which is like Columbus. Now, if someone from China or someone from India is trying to use that application, they have to like their network request has to hit all the way from there to Ohio here, which is a huge latency. So what you can do is you can host your websites on content delivery networks, which will distribute it all across the world. So there would be a bunch of servers in India, in China, in Australia that are hosting these assets that your users can just directly talk to. Now, why would you use this? Once again, there's no setup here. You just upload some files to a cloud service and they do the distribution part for you. Very low latency. So again, instead of a user in India making a request all the way to Ohio, they are only making a request to some other place in the country. I don't know where the service would sit. This is great for websites and any sort of applications because they are available really quickly to your users, which offers a really nice performance. For media assets, so again, images, videos, so like YouTube probably has a huge content delivery network, and it gets really expensive for them, which is probably why they decided to like make 4K videos only available to paid users. But yeah, any kind of media assets you want them to be quickly available to your users, you will put them up on a content delivery network. Same graph. Once again, you just have to like think about your application and not what it needs to be on the cloud. Let's quickly talk about build. This is, I don't know, I kind of feel like I shoehorned this in here, but it's a pretty important thing to think of. These are servers that like once you push your code to GitHub, these servers will pull that code, they will build it, they will run some checks on it, run tests, and then they can deploy it wherever you need. They are great for long running tasks. Again, like the time from when you clone a project to when you are ready to deploy it might be 5 minutes, it might be 15 minutes. So these are servers that are optimized for those long running tasks that are like usually executed in multiple steps. They're also good for event driven or scheduled tasks. For example, when you push a code, that's an event that the server is listening to. Or there could be other events like on some other cloud service, you updated some data or you updated an Excel sheet, and that should trigger a build. Or every night, you clone my code and run all these tests, things like that. Again, they're optimized for fast workflows. So they don't need a lot of storage because all they're doing is cloning some code, running some operation, and then pushing it away. So they are really optimized for that compute performance. They're great for continuous integration or continuous delivery. Continuous integration means that you're always pushing your code, or you're like every 5 minutes, every 10 minutes, something like that. You're always pushing your code to a central repository, and then it's constantly being checked. And continuous delivery is making sure that your code is always stable. It can always be released. So every time you make a push, it's running all the tests. It's going through a bunch of processes to make sure that it's working correctly. You can also use these for different environments of your application. So for example, if someone else makes a pull request, you can have a preview environment ready to see what it looks like before you actually merge it in. Once again, it kind of looks like this because you just write some code or some configuration file that defines what this workflow is going to look like, but you don't actually do the part of like how it's going to run on the cloud or what needs to be installed for that. It's all managed by the build services. Messaging queues, these are like some of my favorite services because I like to build event-driven architectures. But what these services are a way to send asynchronous messages to other systems. So this is in contrast with something like an HTTP request, where if you have one service making an HTTP request to another, it is trying to establish a connection and then waiting for its response. With asynchronous messages, there is a third system that sits in between that acts as a mediator. So instead of you reaching out to this other service, you're just reaching out to the messaging service, giving it a small message, and then you can continue doing whatever. And then it's the job of the messaging service to deliver that message to this other server that you, or this other application that you have. They're great for decoupling these two different applications, which you can call consumers and receivers. Actually, consumers and receivers are the same thing. It should be consumers and producers. My bad. So consumers and producers, again, like producers is someone who is creating a message, creating an event. Consumer is someone who's listening for that or who wants to consume that message. And they don't need to know about each other. So for example, for making an HTTP request, you need a URL, you need an IP address. For messaging, you don't need that. You only need the IP address of the messaging service and nothing else. And you also don't need to know what they're running, what their protocol is. You just need to send that message. They're fault tolerant. So for example, if your application goes down, you cannot make an HTTP request to it, you will fail. But in a messaging system, if the consumer goes down, the messaging system will take that message and hold on to it. And when the consumer comes back, it will deliver that message to it. So this way you don't have any broken workflows, you don't have to crash. Now, why would you do this? Again, messaging services are something you can just install in a virtual machine and use yourself. But the cloud versions, they scale automatically. So you can go from 1 message per day to 1,000 messages per second, and they're fine with it because they can automatically scale. They're great for event-driven architectures, like I mentioned earlier, where you have a bunch of different applications sending messages to each other instead of like making HTTP requests and slowing down a lot. Microservices, which are like kind of a extreme of distributed systems, where you have really small applications that do one thing. And if you're building microservices, you should definitely be like building event-driven workflows for them. They should not be talking to each other with HTTP requests. And they also look like this because they're pretty similar to databases where you don't install anything. You just go and request a messaging service like Kafka or RabbitMQ, and you get that. And you can just write your application on top of it. Do you have a question? No, SMTP is different. SMTP is something you use to send emails to someone. This is to send a message to another application, another program that is going to process it. Workflows are kind of the opposition of event-driven, where in an event-driven system, like a bunch of different applications or software, like they produce events and some other consume them. Workflows are the opposite, where they define a complex workflow in a very simple syntax. And this workflow can include like a bunch of different applications that you're using. A lot of these services allow you to build them visually. So you can like drag and drop and use colors and type it out a bunch of things. But they also have like different syntaxes or different configuration and programming language SDKs to build workflows. Workflows are also great for decoupling because you can write a workflow separately and you can have the individual applications that handle the individual operations separately. A good example of this is a lot of like asynchronous workflows like e-commerce. So let's say when you go to a shop or when you go to an e-commerce site, you hit the checkout button. Now that can trigger a big asynchronous workflow that has to do a lot of things. For example, it can, I'll just give like an example off the top of my head. It might need to go to some sort of an inventory service and check if the product that you're buying is really available. And when it comes back, if it says it's not available, then you first have to fail the checkout. If it is available, then you would probably go to some sort of a payment service and request a payment with the customer's credit card. Once that payment is authorized, you would have to go back to inventory service and find an appropriate warehouse where that product is located. And once you find that warehouse, you would send a request to the warehouse saying that, hey, find this product and make it ready to ship. And then you would also have to go to a shipment service like a FedEx and say that go to this warehouse, pick up this product and deliver it to this address. And finally, once you get the response from the delivery service, you send an email to the customer saying that your product is being shipped, here's the tracking ID. So these are the kind of workflows which you would need to, which are like often difficult to build if you're building them directly into the application. So it's a good practice to build these workflows separately and have all of those individual operations run in separate containers. Centrally defined. So once again, these instead of event-driven workflows, there is this one place that you can look at that shows everything about how checkout works. Works pretty similar. I don't think I have to explain this part a lot. Functions. So these are functions or serverless functions, Lambda functions, cloud functions. There's a bunch of different names for this. These are the poster child of serverless, as I like to call them. What functions basically are is that you would write just a function in whatever programming language you like, and you would deploy it to the cloud. And you can specify what are some events that would trigger this function, and the cloud service will do that for you. Just a function, nothing else. These are pretty useful for like lightweight one-off computations. So for example, I can't think of any good examples right now, but something that at Revolution we use functions for is that when a bunch of different cloud services like GitHub or Heroku, they can trigger a webhook or an event. They send a request to one of the functions that we have deployed, and that function will send a message to us on our Teams channel notifying us that this happened on Heroku or this happened on Travis. So these are pretty useful for something like that. Or you can build your entire applications in this event-driven architecture style. You can have, so something like I mentioned, the checkout flow. Each individual step of that checkout flow can just be a function instead of being a whole app on its own. Building simple APIs is also useful for it. In fact, I think this is what most people use functions for. It's building simple HTTP APIs that would be used on some front-end applications. They're great for unpredictable traffic because if you're just running a function, the function is not run all the time. If that event is not being triggered, the function is not running and you're not paying for it. But if you have a sudden burst of users and you suddenly have 5,000 people who are making a request to that function, it can just do that. And you will only pay, again, you will only pay for when the function runs, not for like a 24/7 running machine. So it usually depends on pretty low cost. What's up?
So like for example, like the recent case of Ticketmaster, okay? Mm-hmm. If it had like functions on the database, mm-hmm. So then how would still crash even though like it will depend on the function or like.
Can you explain what happened with Ticketmaster? I don't think I'm aware.
Like Taylor Swift, like she announced like her concert, mm-hmm. And like her tickets were there on Ticketmaster. Like the site immediately crashed after like 2 hours or something.
Right.
It was a pre-sale ticket, so like and it crashed for some reason.
Like 14 million people like started to like get in the queue to buy the pre-sale ticket.
Right.
And because of that, the site crashed.
Got it.
So like even though they might have like considered the fact that it will be overloaded, it's still like, overloaded the functions as well. So like, do you know what would have happened or like the solution for that?
I mean, the solution for that is just to have a better architecture, and serverless is one of the ways to do that. But so serverless functions is one of the ways to have scalable architectures like that. Serverless functions you would use for your code, but you still cannot use it for database. You still have to make sure your database can scale to millions of users or whatever. And any other piece of architecture, like you would you might have some queues or pub sub or things like that. You might have workflows, and all of those should be able to scale like this. So I don't know enough about the situation to just like give you an answer on what they should have done, but usually like a better architecture is needed to like solve scalability problems. What's up? Okay, we can talk about it after this. So for functions, it kind of looks like this because it drastically reduces the amount of application code you have to write, because now like if you have used Node.js and Express in the past, you would know that you need to create a router, you need to add middleware, you need to like add handlers to each API route and things like that, and then you need to run it on a server. But with functions, once again, you're just writing a function that responds to an HTTP request. So it really like you have to write a lot less code for that. There's a bonus here for edge functions. So I just talked about content delivery networks and how they distribute static assets to edge servers all around the world. Well, edge functions do the same for serverless functions. You can write functions that can be deployed on edge or like global network of servers, and they can be like pretty close to your users. They offer extremely low latency, and they have to be lightweight because like edge servers are not super powerful, but they can run it pretty fast, and they're pretty low latency, like I said, because a user from India should not have to go all the way to, or should not have to request some resources all the way in the US. They can just do it in servers in India. Why would you use this? So this is great for localized features. So if you want to cache some data depending on the location, these edge functions are great to do that. They're great for like middleware to like kind of transform the request when it comes in or redirect them somewhere else to check if they're authenticated or not, and just redirect them to a login page instead of going towards the application, because it has pretty low latency. They have extremely low cost because somehow edge servers are much cheaper than like big data center servers. And obviously the benefits from serverless carries on here, which is that you only pay for when a function is running. You don't pay for 24/7. You only pay for the 100 millisecond or something that your function will run for. They are good for very light workloads. I think there is a lot of work going on in edge functions to change this. In the near future, you might be able to pretty much deploy your entire applications on edge functions and not have to worry about like centralized locations at all. They look the same because from your perspective, you're not doing anything else. It's just an improvement on the user performance. So,
if I have an API that has 50 endpoints, that 50 functions, or that 50 gig?
it's so the question is, if you have a function that responds to an endpoint.
Like you talk about, we can deploy REST API as functions.
Yeah.
I have a lot of endpoints in my API, so how would it scale in a function? That be one function, for example.
So you can, okay, so the question is like if you're deploying a REST API, something like a REST API with 50 endpoints, do all of them go in a single function or in separate functions, right? So my answer is that it's a spectrum. You can decide which one you want. You can deploy them all in a single function if you want, but you have to like do a lot of, you have to do the route matching on your own. And I think you also, like it becomes a pretty big function. The thing with functions is that there is something called cold starts, which is that the cloud service that's running your function might just go down, and then it'll only come back up when you make a request to it. So the larger your function is, the more time it takes to start up. But also speaking from a function perspective, like if it's a huge function, if it takes a lot of time to compute, then you're just wasting resources. So there is a sweet spot in between where like you can have 5 to 10 endpoints in a single function and deploy them all like as different functions. That would be the sweet spot. Go ahead.
So when you send a request into a URL, how does the function manager know to map your function? A big routing function that you
usually the cloud service will have another service to do that. For example, AWS has API gateway, and Vercel has their own thing where with like Vercel has file-based routing, so every file gets converted into a function. I'll talk more about this later, but yeah, these are like the cloud service that you would be using for function has their own way to handle routing to it. Or if you want to deploy all of them into a single function, then you have to do all the routing all yourself. Yeah. What's up?
Hey, I didn't know about hedge funds. I was trying to think what the use case would be. Can you integrate serverless functions with hedge functions?
Yeah, that's the most common way to build apps right now, is to like have both edge functions and serverless functions. Another thing that I'll touch on soon. Do I have time? Yeah, I'll need to run through this a little quickly. Okay, so edge functions, talked about that. So let's now talk about some specialized capabilities. So everything else that we talked about so far are basically like a way to like write an application and deploy it to edge or deploy it to the cloud. With specialized capabilities, it further reduces the amount of code that you have to write. So we'll start with auth, but there's a lot more of these. Auth is like providers for authentication. So for logging into an application, for sign up, for user management, things like that. Magic Links, OAuth, they support all kind of authentication methods. And there's also authorization, which is basically roles and permissions. What does a logged in user have access to on your application? So these are available through really simple APIs. So you don't have to like build the entire authorization management from scratch. You can just go to these services and say that I want auth in my app. This is how they log in, or that the service will tell you this is how they log in. You just have to call that login function. How to use this? Again, this is difficult to implement. I have implemented like auth from scratch on at least 5 projects, and I don't recommend it. There is way too much going on. It's a solved problem. Just go and use these services. Security and reliability. This is like auth is a very important part of your infrastructure. If that goes down, no one else can do anything. You need a lot of security here. So again, don't spend your time on it. Just go and use these capabilities. All green, because you don't have to write any code to handle auth. You just write your application, and these services will give you all the built-in features for auth. Yeah, Auth 0 is one of them. Recently, I've been using Clerk, but yeah, Auth 0, Firebase, Supabase, they all have some sort of auth capabilities. Real-time is another one. This is communication with multiple front ends. So this is where a lot of different like instances of your client need to talk to the server, and they all need to receive updates. These happen through WebSockets usually. These are useful for live data. So if you, example, if you have dashboards that need to be updated in real time, maybe their financial data, maybe their like tracking data for your infrastructure. Chat apps, this is like the most common example for real time, because if you send a message on a group chat, you want everyone who is in the group chat to instantaneously receive that message. So you need real-time capabilities for this. Real-time dashboards, like I mentioned, is another big use case for real-time capabilities. Push notifications is another one, where if once your users install an app, you might want to send them notifications about updates, offers, whatever. And again, these services are scalable. If you implement it on your own, scaling real-time services is like, it's the biggest pain compared to everything else. Like scaling databases and real-time are the hardest things. You can even scale containers pretty easily. Once again, this is all green because there are some services that give you really simple APIs to implement real-time capabilities. IoT is another one. It's kind of similar to real-time, but they have much more lightweight protocols that you don't have to like, because HTTP servers and HTTP requests, I think, take a lot of resources. They're pretty consistent, reliable, and you can use them for smart devices, for recording updates on your databases, to monitor, to update them, to like update their firmware. Also all green. And there's also some cloud services for machine learning. What do? They make developing and running machine learning algorithms easier. How do you use them? They make machine learning easier. I don't know anything about machine learning, so I cannot say much. and I'm pretty sure it's all green, but yeah. These are like a few of the specialized capabilities that I've talked about, but in reality, there's like hundreds of them. Just like scroll through AWS's product page, or don't. It'll probably give you a headache. Yeah, so that was all I had about specialized capabilities. Let's talk about some patterns. So just a few seconds ago or a few minutes ago, we were talking about combining edge functions and serverless functions together. Now, there are patterns like these because obviously when you're building application, you're not just building like a compute application. You're going to need multiple of these services. So let's see how some people decide to combine them. Bare metal, it's not really a pattern. A lot of people just like get virtual machine instances and do whatever they want with them, and they individually deploy to each machine. Usually, not usually, like we would individually deploy to each machine if we have very small workloads. But at scale, you might want to like get a bunch of different machines and run some sort of container orchestration like Kubernetes on it, so that you can deploy to containers instead. This is practically the cheapest option because you have to pay the least amount of money for like the hardware or the capacity that you're using, but it's also the most manual work. So it's the cheapest in terms of money. It's the most expensive in terms of time and effort that you're spending. This is what it might look like if you're like renting, or if you're getting one server to run everything that you have on it. Or for on scale, this is what it might look like, where you have a bunch of servers and a platform like Kubernetes on it, and then you can run as many instances of your application or your database as you want on them. Because at the container platform layer, you are not thinking of the physical servers anymore. And then we enter containerized plus managed services. So what this is your app runs as containers on orchestration platforms, like you see on the left. Again, they're scalable, so you can run as many of them as you want. These are usually stateless, which means you are not storing any data in memory or like in variables, in global variables, things like that. All the data should be stored in external services. And these external services, like you see on the right, are managed services for data storage, cache, messaging, and whatever. So you're really only focusing on that app part here. Again, these are great for granular services where you would break apart your entire application into smaller pieces that can be separately deployed and also separately scalable. So for example, if I break my e-commerce application into a checkout service and a product catalog service, a lot of people are going to look at the catalog than checking out, right? So I would want 3 instances of my catalog service, but only 1 instance of my checkout service, so that I can serve the larger workload of people, or the larger amount of people that are just browsing instead of buying anything. And this is the most easy and the most popular way to deploy apps. And then we have pretty much the same thing, but we switch out containers for functions. And this can be both regular serverless Lambda functions and edge functions. These are also stateless, so you don't really store anything in memory. You just receive a request, you handle that, and then you're out. Once again, we have managed services for everything else. These are very granular function servers. So instead of like having a container that handles product catalog, I have a function for recommendations. I have a function for searching. I have a function for sorted or filtering, things like that. So these will be very granular, and these are usually the most scalable because you have these granular functions. The platform can decide which one should be scaled more. So if you have no one checking out for a month, the checkout function just won't run and you won't pay for it. And also modern full stack frameworks are really optimized for this kind of deployment. I'll go into this into a bit more detail on this when I talk about providers. And of course, you can use edge functions for even more performance. Then there's this pattern called backend as a service. Here you can see just the absurd amount of green. This is usually a single service that provides all the capabilities that you need in a single simple API. And this has functions to run on the backend, content delivery, data, auth, real-time stuff, really anything that you need for your application. These are great for full stack web mobile apps that you're building. So you can focus almost entirely on your front end code. And you can see that there's only one little orange app here because you only write a few functions when you need some sort of a backend logic. If not, you can just focus on your front end code. These are pretty easy to set up and deploy, but the biggest disadvantage is that you're logged into that vendor. And once again, I'll go into this into a bit more detail soon. We have a bonus pattern. This is not really a pattern. This is more like something that an easier way to deploy to all of these separate patterns. These are like cloud infrastructure. So instead of going through some sort of web UI or using CLI commands, you would just define your infrastructure in your code or as configuration files. These can be files like JSON or XML. I hope no one's using XML for this. Or some special syntax like Terraform or SDKs in your programming language. Like you can write a JavaScript file that you can write some code in JavaScript that knows, or that is basically used to like spin up containers or spin up servers or databases for you. And that means that you get help of all the developer tooling. I won't go into this too much because I need to run through this. Oh, we have a jackpot. This is called self-provisioning runtime. That is coming soon. I'll make a separate video about this. I definitely don't have the time to go into this. Okay, so our final topic are talking about the actual providers that provide these services. Let's start with the one-stop shop. The AWSs of the world, the Google Clouds, the Azures, they literally have like every cloud capability that you can think of. If they don't, send them a message and they'll probably add it in the next week. These almost always own their own data centers, and you can use their proprietary services for like the best integrated experience or the best experience for that cloud. So for example, on AWS, you can use Aurora for a good relational database. You can use DynamoDB for a good NoSQL database. You can deploy your functions to Lambda. You can use simple notification service for PubSub. Or you can use standardized services so that you don't have to be logged into that cloud. So for all the same examples, you can use something like MySQL, MongoDB, and Kafka, which are like open source services which you can deploy to any cloud. And this lets you not be logged into that one service, but they have a little like worse experience, worse integrated experience. And these are the companies that I listed above. Then we have cloud services that offer just one or usually two specific capabilities. For example, for databases, you have these services. For real time, there are separate services. There are separate services that provide cache, messaging, queues, schedule jobs. And the benefit is that they usually, I don't know why, but they have better developer experience than the providing everything, the one-stop shop services. But obviously, they lead to a worse integrated experience for everything. And this, because you get into a state that I call product hell, where you're now using 5 different services for 5 different things, and you have to keep track of that. Or worse, the more application scales, you're probably using 20 of these, like that. But these exist, they're pretty useful. Then we have broad capabilities, which now these are names that I'm just coming up with. They're not really official terms for anything. So don't go on Twitter talking about like this is a broad capability service, not a specific capability. It's not a thing. But actually, a lot of people call these platform as a service or PaaS. These provide many of the essential services for hosting apps, which means computing, data, file storage, cache. So a lot of these services will provide like at least 3 of these. They have a decent integrated experience because you are just using that one cloud service. You don't really have product hell. And there's almost no vendor lock-in because you're just deploying to containers and you're using standard SQL or Mongo or something like that. You can just move from one of these to another without really a lot of work. Here are some pretty good examples that I like. Flight control is the only one that didn't have a light background logo. So please change that if you're watching this. Then we have backend as a service providers. So I talked about the backend as a service pattern. This is, again, great for mobile apps, web, or like front-end heavy web apps. Mobile apps is really the one that launched like this revolution in cloud services. And they have like almost all the backend capabilities. So messaging, databases, storage, authentication, and you only have to write backend code when you really need to. They're pretty easy to configure and set up. Here are some examples. And they have really the highest vendor lock-in because you cannot just move from Supabase to AppWrite or to Firebase. So this is really the biggest argument against these services, is that you're logged into what they or how they do things, and you're logged into their pricing model. So if you can accept that, then it's a pretty nice developer experience. If not, you should probably do this, which is the serverless web, or it's kind of like a bunch of different paradigms that I try to combine into one. But really the core of this are like some basic principles, which is static front-end hosting. So your front-end assets are on CDNs so that they are highly available to your users with very low latency. And your backend APIs are almost entirely hosted on serverless functions so that they can be scaled up and down as you need. Vercel and Netlify are like the two big players in this space. But really the more important thing here are the frameworks which you would use to develop these kind of applications. So Next.js is the biggest one in here. Remix is another big one. Solid Start is the one I'm playing with soon. They are extremely scalable because, again, you deploy to serverless functions, not virtual machines. So they can be scaled as much as you want. Very low vendor lock-in. Here you're not logged into the cloud platforms at all, really. You're a lot more logged into the framework you're using. And a lot of these cloud providers just know how to deploy an application written in Next.js or Remix. And here are the two big players. That was a lot. Now what? I'll try to summarize if I really like, this is the slide that I had the most difficulty with, honestly. There's a cloud service for pretty much everything. That should be the big takeaway. Any kind of capability that you're looking for, there probably is a cloud service for it. If you're like starting a new application, if you're starting a new project, backend as a service providers are the fastest to get started with. Or like they provide the most capabilities without you having to do any of the work. There's some learning curve there, like you do have to spend some time learning how their API works, and there's vendor lock-in. But if you accept those two things, they're really the fastest. If you want to learn cloud services, learn for the job. Again, there's service for everything. So look, if you're going for a specific job or a specific area of the career, see what kind of cloud technology they're using, which is probably going to be AWS anyways. So, something more React friendly. So like all the frameworks that I talked about in the serverless web area, Next.js, Remix, Redwood, they all use React. And almost all the teams use React, all the projects use React. So just learn how Vercel works or how those framework works. When it comes to databases, SQL is still king. So you don't really need to know how a lot of the specific database providers work, because most of them just use SQL, and most of the companies also just use SQL. You should have learned about containers yesterday. So containers is really like the basis of all cloud. So if you don't know about containers, play around with Dockers, play a bit, container platforms like Render or Fly.io. I would have said Heroku here, but rest in peace. But you don't really have to know a lot about containers, about how they're spun up, about how to create, what images are. Those things are really managed by the cloud services. And if you haven't learned about functions already, go learn about those. Serverless functions are great. Go build something on Lambda. And yeah, I think that's pretty much it. If you have any questions, let me know. And or just send me a message on LinkedIn or Twitter or Discord. Thank you. Anyone online questions?
That's good. Let's chat, yeah.
Dev, chat yet? Okay.
No questions for me. Thank you.
Thank you, Professor, for coming. Does anyone have any questions online? Right. So with that, we can end the meeting here. Just want to go through some final slides. To check out our sibling organization, AAA, ACM Women, ITSA, Women in Tech. I don't know the schedule on the top of my head, but they all have pretty active Instagram page. Thanks for coming. Please take attendance at acmuc.org/. That goes to people online too. So yeah, thank you. Thank you, Benjamin, for coming. So I'm going to stop the recording.